Hello and welcome to the 9th video, well 11.9 at any rate, integration for Year 2 Edexcel A-Level Maths. So we've looked at an absolute plethora of different integration techniques, integration by parts, reverse chain rule, using partial fractions, but sometimes there might be an integral where we just don't know what to do with it at all, and if that's the case where there's no algebraic technique to be used, we can actually approximate integrals numerically, in which case we're looking at today. The trapezium rule. There's a few different ways of evaluating integrals numerically, but the trapezium rule is the one we're going to look at today. So, question 1 is designed to get you thinking about why the trapezium rule and the formula for it looks the way it does. And question 2, which I'm going to show you here, is revising integration by parts. So pause the video now and try these on your own, and when you're ready to see the solutions, press play. And hopefully the warm-up solutions, in particular question 1, will make sense for later in this video. Okay, so let's have a look now together at solution to warm-up question 1. So, 𝘢𝘱𝘱𝘳𝘰𝘹𝘪𝘮𝘢 wants to approximate the area under a curve shown below here by using 4 trapezia. I've shown these in red as well. The original curve's in black. So he sets the width of each trapezium as equal, calling this value h, and labels the heights of their parallel sides in terms of y using subscripts as shown below. So the first vertical height at x0 is given by y0. And the y value at x subscript 1 is y1, and so on. So anyway, using this idea, he's got 4 different trapeziums, each with width h. So he's going to use h to be 10. And he's going to use a formula for the area of a single trapezium. Area of trapezium is half a plus b multiplied by h, where a and b are the parallel edges of the trapezium. We need to show that 𝘢𝘱𝘱𝘳𝘰𝘹𝘪𝘮𝘢 approximation for the area under the curve between x0 and x4, given the 4 trapezia, is given by this formula here. So let's just build it up using the formula for the area of each trapezium. So the area is going to be approximated by the areas of these 4 trapezia. So the first one is going to have an area of a half y0 plus y1 multiplied by h. Trapezium 2 is going to have an area, similar idea of course. So trapezium 2 is going to be a half. The 2 parallel sides for trapezium 2 are y1 and y2. So that's y1 plus y2 multiplied by the width. The next one, trapezium 3, that's going to be given by a half y2 plus y3 multiplied by h. And the last one, last but not least, trapezium 4, which I'm going to do in purple, would have an area, of a half brackets y3 plus y4 multiplied by h. Now we can rearrange this because actually what we've got here is a half times 10. But h is 10. This is a factor of each of these expressions. So I've got a half times 10 there, because h is 10. I could have just called that times by 10 to begin with, really. Don't know why I didn't. So this here, I can factorise out immediately at the front of each of these. So I'm going to get a half times by 10. Then in brackets, I'm going to get y0 here. Then I've got y1 plus another y1, so I've got 2 lots of y1. y2 plus another y2, I've got 2 lots of y2. Then I've got y3 plus y3, which is 2 lots of y3 again. So all these ones are doubling up, apart from the first one, y0, and there's only 1 lot of y4. So just rearranging this ever so slightly, I've got a half times 10. The first height plus the last height plus 2 lots of all the heights in between. In our case, y1, y2, and y3. So that's the specific formula for Narcís, where he's got 4 strips and each one has a width of 10. For part B, let's try and generalize this so we can get a general result for n strips, each of width h being used. Let's get a formula for the total area, or an approximation I should say, to the total area in terms of h, y0, y1, y2 and so on. Well, if we look here, if we go for a general width h, well, in our specific case, our h was 10. So to generalize, instead of being half times 10, that just becomes a half times h. We've got the first height and the last height, so generally speaking that'll be y0, and if you have n strips generally, that'll be yn, the last one, and 2 lots of all the heights in between, y1 plus y2 plus y3, all the way up to the penultimate height, y subscript n minus 1. I missed a bracket off there as well, which is going to annoy me, so put that bracket back on. And yes, that's warm-up question 1. So that's the general formula to approximate the area under a curve using the trapezium rule. We're going to use this result today for the main bit of the lesson. Warm-up question 2. Use integration by parts to find the integral of 1 minus 2x multiplied by e to the minus x dx. From now on, I'm going to use this method called the DI method. Well, what I'm going to call the DI method. I'll link you to a video in the description which talks through this in a bit more detail. Essentially, we just think about which product we're going to differentiate and which one we can integrate. So using the acronym LIAT, where L is logs, I is inverse trig, A is algebraic, A comes before E, where E is exponential. So therefore, because A comes first in the list, whatever comes first in the list we put in the D column. So because 1 minus 2x comes first, that's what we put here. Therefore, we need to integrate e to the minus x dx. So differentiating 1 minus 2x, that just gives minus 2. Integrating this, we divide by the new power. The power won't change because it's an exponential. But when we divide by this minus 1, so we get minus e to the minus x. So we take the product of that diagonal, plus, minus, plus, minus. All this is explained in a different video if you're not familiar with this particular technique. And then because we can integrate this row, because it's just some constant multiplied by e to some power, we stop at that row. So therefore, 1 minus 2x e to the minus x dx is going to be these two multiplied together, so minus e to the minus x multiplied by 1 minus 2x, and then it's going to be subtracted the integral of negative 2 multiplied by negative e to the minus x. Multiply these two together gives a positive, because minus times a minus gives a positive, so minusing away 2 lots of the integral of e to the negative x with respect to x. So next step, I'm going to expand this out. So I'm going to get 2x e to the minus x minus e to the minus x. And this here, integrating e to the minus x, as we saw here, generates a negative. But because we're doing a subtraction anyway, minus and a minus again, that's going to give us plus 2 e to the negative x. Then, of course, plus some arbitrary constant of integration c. And finally, just to simplify and collect terms, we can hopefully see here that we're going to have just one lot of e to the minus x overall. So we've got 2x e to the negative x minus e to the minus x plus 2e to the negative x is, as I say, just positive one lot of e to the negative x, then plus c. So now we've had a go at the warm-ups, let's have a look at how to find estimates for integrals using the trapezium rule. So the trapezium rule to approximate areas under curves. The main bit was actually what we saw in the first warm-up question 1. So despite there existing a plethora of methods and techniques to evaluate definite integrals in areas under curves, in some cases integrals are incredibly difficult to solve algebraically, and indeed at times would be impossible. So in these cases, an integral might call on us to use numerical integration to approximate a definite integral. And although there's many algorithms and methods which fall under the umbrella of numerical integration, for this course, we're just going to focus on the trapezium rule. So imagine you have a generalized curve here, which is continuous on some interval of x from a to b. And imagine evaluating the height, basically f of x, if this is a graph of y equals f of x, for heights at different points of x. So if we divide x in between a and b into n different strips, each one with an equal width, and so each width would be the difference in between b and a divided by the number of strips. So h is b minus a all over n. But to generalize what we saw in Warm-Up Question 1, if we've got to work out the area between the x-axis and the curve, in between x being a and x equals b, the area is approximated by this expression here. So it's going to be half times h, y0 plus yn, plus two lots of all the other heights in the middle, where h equals the difference in between b and a, all divided by n. A couple of other things to consider as well when forming this approximation using the trapezium rule, because we need to consider if our approximation will be an overestimate or an underestimate. So what we can say here, if f of x is concave between a and b, so it sort of flexes outwards like a cave, the trapezium rule is going to underestimate the area of the curve. So a little image to help. This is a concave curve in orange, sort of curving outwards. A trapezium in between these 2 points here, as you can see, although approximates the area in between this line and that line, does give an underestimate because this bit here isn't included in the area of the trapezium. If, however, the curve is convex between a and b, we're going to get an underestimate, an overestimate of the area under the curve. So if it's convex, like so, sort of punched inwards, I think of it as, then a trapezium in between these 2 points, call them a and b for example, that's going to overestimate the area under the curve because we've got this hidden bit here, which hasn't been included in the area underneath the curve. So just two different things to bear in mind. These might be 1 markers in evaluating questions in your assessment and exams. So let's have a look at some questions, just 2, showing this in action. So, quick example 1. We've got a diagram to the right showing a sketch of a curve y equals sec of x. So the finite region R is bounded by the curve, the x-axis, and the lines x equals 0 and x equals pi over 3 as shown. The table shows the corresponding values of x and y, for y being sec x. So for part A, all we need to do is complete the table with the values of y corresponding to x being pi over 6 and pi over 4, giving answers correct to 3 decimal places. So this is fairly easy to work out. And so when x is pi over 6, what we're needing to work out here is sec of pi over 6. Well, sec is obviously 1 over cos. So if I do 1 over cos pi over 6, so shift pi over 6, close the brackets, that's going to give 2 root 3 over 3, which, if we just simplify it as a decimal, gives 1.155 to 3 decimal places. So when x is pi over 6, we've got 1.155. And when x is pi over 4, we can just go back and toggle, change the 6 to a 4. That's root 2, which to 3 decimal places is 1.414. Then B, it says use trapezium rule with all the values of y in the completed table to obtain an estimate for the area of R, giving your answer to 2 decimal places. So this case here, we've got how many bars? We've got different strips. We've got 0 here, as you can see. We've got one where x is going to be pi over 12, which is there, pi over 6, pi over 4, pi over 3. So x being equal to 0, pi over 12, pi over 6, pi over 4, and pi over 3. So that's just trying to show you that although there's 5 different values, the number of strips is actually going to be 1 less always. So in our case, h is going to be the difference in between this bound and that bound. So it's just pi over 3 divided by how many strips. So because there's 4 strips, h is just pi over 12. So for b, the area is going to be half of h. So it's going to be, I'll write down the half explicitly so you can see where it's coming from. Half times pi over 12, so that's our h. And then we use the y values. So the first y value, y0, is just 1. The last one is 2. Then we do 2 lots of all the ones in between. So 2 lots of 1.035 plus 1.155 plus 1.414. So if we try this on the calculator, so we've got shift pi over 24, whoops, and then press brackets, so 1 plus 2, then 2 lots of the middle ones, so 2 lots of 1.035 plus 1.155 plus 1.414. That gives a value to 2 decimal places, 1.34. Now part C is asking us, with a reason, if this estimate we just worked out 1.34, if that's going to be an underestimate or an overestimate. So as we mentioned earlier, if a curve is convex, which this one is, because it's sort of caved inwards, sort of bent inwards rather, the trapezium will always give an underestimate, sorry, an overestimate, I mean to say, wake up, of the area under the curve. If I was to just show you the trapeziums here, can't really see because it's so close to the curve anyway, but this would ever so slightly overestimate the area. If you can see that here, if these lines were slightly thinner, that would be a bit more included than what would just be the bar. And so when it's convex, we're going to get an overestimate. So conclude with C, keep it simple. It's an overestimate since the graph is convex. Work example 2, this one's just been taken from a shadow paper actually. So this time, we got the speed of a small jet aircraft. It was measured every 2 seconds, I should say measured, apologies, starting from the time it turned onto a runway until the time when it left the ground. And the results are given in the table below, with the time in seconds and the speed in meters per second. So using all of this information, first off for part A, use the trapezium rule to estimate the length of the runway used by the jet to take off. I'm going to read part B as well before going on to it. It says, given that the jet accelerated smoothly in these 10 seconds, explain whether or not your answer to part A is an underestimate or an overestimate of the length of the runway used by the jet to take off. I wanted to include this example because it's potentially very confusing. Nowhere in this table does it say anything about lengths. In fact, it's not even particularly obvious to some people this would be a trapezium rule question at all. The key thing is, I would suggest to actually sketch a graph of what's happening. So speed and time, and using what it says here, that the acceleration is smooth, this will be a smooth curve like so. It goes back to physics lessons in GCSE. Maybe you're still doing physics for A level, in which case you definitely should know about what the area underneath the speed time graph represents. So the area underneath the speed time graph, it represents the distance travelled. The best way I think of remembering this is area, we're basically multiplying 2 dimensions. So the dimension along the x-axis is a time dimension. So if I take seconds and multiply by the dimension on the other axis, speed, that's meters per second. Simplifying the indices, s and s minus 1 cancels, and so it stands to reason that the area underneath this graph is going to relate to something with dimensions of meters, and it certainly does because length or distance is measured in meters. So that's how I always used to think about why it is distance travelled. So without using that idea, you can't really go anywhere into the question. Anyway, the trapezium rule to estimate the length of runway used by the jet to take off. So simple enough. So part A, the area is going to be a half multiplied by h. Now this time it's measured every 2 seconds. So you can see here, because the gaps are in 2's, h is just 2. So the speed at time 0 is 2. The final speed is 26. And I do 2 lots of the middle speeds. 7 plus 9 plus 13 plus 22. Close off and input that into the calculator and see what we get. So, half multiplied by 2, and I could just put 1, but I'm just trying to show you step by step. 2 plus 26, then 2 lots of 7 plus 9 plus 13 plus 22. And we get 130. So that's 130 meters in 10 seconds. Always think as well, if it's a question giving a context where we can use common sense, always be thinking, if possible, does the answer make sense? Jet aircraft in 10 seconds, could it go 130 meters? It certainly could if it's just about to get ready to take off. Usain Bolt can do, or any these days, world record level or world-class sprinter can cover 100 meters in about 10 seconds. So 130 for a vehicle, definitely possible. Part B, again similar to works example 1 part B, explain whether or not your answer to part A is an underestimate or overestimate. Again, because this curve is convex, if we did a graph of speed and time, the trapezium rule again would give a overestimate. So we just have to say this in similar words. Part A is an overestimate since the graph of speed versus time would be convex. So now it's over to you to try some of these on your own. So in the book, exercise 11I on page 320 gives a few very good questions. Try all those, check your answers at the back, and if you're struggling, do let me know, and keep going. So until next time, I'll see you very soon.